By now, you're probably really tired of me spending a whole bunch of time drawing out these orbitals, right? So when I talk about lithium and I ask you, okay, what does a lithium atom look like? And then you tell me, oh, it's an s orbital with one electron in it. And then I draw that, right? And that one's not so bad. That one's, pretty fast to do. But then I say, okay, how about if I had a, what did I say this one was? Lithium. Let's do lithium. And then what if I said, what about if I had a fluorine atom? And then you say, okay, well, there's two electrons in the s orbital, and then we have our p orbitals, and then I have to go in here and draw that out. And I'm like, okay, well, here's one p orbital, and then here's another p orbital. And then I'm like, hold on, I'm almost there. Just gotta get my third p orbital in there. And then I have to put my electrons in. So there's always two in the s for fluorine. And then there's five more in the p orbitals, which leaves one open space. Anyway, we've talked about this so many times. I've drawn this so many times, but I bet you are ready to move past this very drawn out process to write what the valence electrons look like in an atom. Now, why did I say valence? Because remember that valence is that word that we use to talk about the outer electrons, right? So the electrons in the outer shell or highest energy level. And so if we look at lithium, for example, we know that lithium doesn't have just one electron. We're just seeing one electron because it's in the valence shell, right? It's the valence electron. So I want to show you a super duper easy way to write the valence electrons for an atom. And what I'm going to do is I'm going to teach you a really specific way to do it that I'd like you to follow because it will help you when we get to a little bit more complicated, complex things. So the simplified way that we're going to use is called a Lewis structure. So a Lewis structure is a way to show the valence electrons. Shows the valence electrons of an atom. This is when we're doing it for individual atoms. You can actually make much more complex Lewis structures, and we'll get to that in just a moment. But for now, let me show you how I'd like you to write your Lewis structures. So what I want you to do is you're going to imagine that there's a box around the element. So let's do hydrogen first. You write the element symbol. So in this case, it's just the letter H. And then you're going to draw a box around it. Now, I will say this right now. You're not going to draw your box for very long. The box is literally just for right now for me to demonstrate how to draw it, but really we won't end up drawing that box around it in just a few minutes. So when you're filling in the electrons around it, you're just going to put the electrons on the sides of the boxes. So hydrogen is going to have one electron, right? And I know that because it has an atomic number 1, and so a neutral hydrogen atom will have one electron. I'm just going to put that on one side of the box. Okay? So if I drew it without the box, it would look like this. And then if I wanted to do, for example, let's go all the way to carbon right here. Now, carbon, we know that carbon has 6 electrons, right? But how many valence electrons does it have? Well, it's got 1, 2, 3, 4 valence electrons. So let's do one for carbon. I'm going to draw my element symbol, which is just a capital C. I'm going to put my box around it. Now, here's the deal. When you write the electrons, or when you draw the electrons around the atom, you're going to put one on each side of the box before you double it up. Okay? You can have a maximum of 8 electrons around it. I'll show you that in just a minute. But when you're actually putting them around, you make sure that you're spreading them out. So you put one on each side of the box before you double it up. So for carbon, we have 1, 2, 3, 4. And if I was going to draw it without the box, I would still just have an imaginary box and draw my electrons around my imaginary box. You see how I'm not putting the electrons here, right? I'm not doing that. I'm putting them around my imaginary box. Let's do nitrogen. So how many valence electrons does nitrogen have? 1, 2, 3, 4, 5. So I'm going to draw a capital N for the element symbol. And then I want to put my electrons all the way around. So I'm going to have to put 5 electrons in. So I'm going to go 1, don't double up yet. 1, 2, 3, 4. And now I do have to double up, right? So let me put it here, 5. I could have put that 5th one on any of them, but I just randomly put it there. So if I did it without the box, it would look like this. Let's do oxygen next. So I'm going to write an O. I'm going to draw my box. So oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and just to show you that it doesn't matter where those double ones go, you could put them anywhere, right? I could put them over here if I wanted to. Right, there are 6. And then let's go to fluorine. I'm going to draw my box around fluorine as well. Fluorine has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. And so let's draw those around. 1, 2, 3, 4, 5, 6, 7. Okay, so let's do that without the box. 1, 2, 3, 4, 5, 6, 7. Now I'm going to draw now 2 special elements. Okay, and I'm going to draw them because they're what all the other elements wish they could be. Let me just draw them here first. So the first one that I'm thinking of is helium. Remember how we've talked about that helium is just super, super stable, that in fact, all the noble gases are super stable. Well, helium is super stable, as we've said before, because it has a filled first energy level, right? And so if I was going to draw helium, I would actually draw both of them together like this for a reason that we'll get to later. But for right now, for helium, I want to show that its energy levels are filled. And so I actually draw the electrons in a pair here. And so let's do neon as well. Neon has 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. Let's draw that. 1, 2, 3, 4, 5, 6, 7, 8. And so what this shows us is that the noble gases have a special configuration. Okay, so noble gases have filled valence shells. And so for most of the elements, everything except for hydrogen and helium, this has a special name, and this is called the octet rule. So let's talk about the octet rule here for a second. These elements here are said to have an incomplete octet. Now, an octet just means that it's going to have 8 electrons, or that it doesn't in this case. So it doesn't have 8 electrons, right? An octet, means 8, oct, 8. That oct is the prefix for 8. And noble gases, it turns out, have complete octets. A noble gas configuration is one where an element has achieved a complete octet, like the noble gases, right? Except for helium, because helium only has that one energy level. But if we were going to draw any of the noble gases, let's do argon. Let me do it in black. If we were going to do any of the noble gases, they all have a complete octet. And so the octet rule states, let me write it, let me scroll down a little bit. So the octet rule states that atoms will form covalent bonds to achieve a stable noble gas configuration. That is, they want 8 electrons. Now, the exception to this rule, as we already mentioned, is hydrogen, right? Hydrogen and helium. Hydrogen, it turns out, and we're going to look at this very soon, but hydrogen can't have 8 electrons around it because it only has the 1 energy level. And so hydrogen likes to have 2 electrons. So hydrogen wants to have 2 electrons, like helium, like its own noble gas. So I want to show you something really quickly because, as we've spoken about before, we won't always have this drawing or this chart, I should say, to show us our valence electrons and our orbitals and everything. But luckily, the periodic table gives us a really, really easy way to know how many valence electrons each element has. It's literally in the numbers. And so if you are in group 1, let me just sort of highlight, if you are in group 1, then you have 1 valence electron. If you are in group 2, you have 2 valence electrons. It gets a little different when you get to group 13. So I want to point something out. Sometimes you might see these written as group 1A, group 2A, and then group 3A over here, group 4A, 5A, 6A, oops, not 6-8, 6A, 6A, 7A, and 8A. The more modern way, more updated way is to have it listed as just 1 through 18, groups 1 through 18. But either way, it works because you have your 3 here and a 3 in the second number here. And so you guessed it, these elements all the way down here all have 3 valence electrons. 3 valence electrons. And so on and so forth, right? So these elements all have 4. These elements all have 5. These all have 6, 7, 8. Okay? And so if I asked you, for example, if I said, how many valence electrons does sulfur have? You just look right here and you say it has 6. You don't even have to think about it or I don't know. Just it has 6. It's that easy. How many valence electrons does calcium have? 2. You don't have to think about it or memorize it. You just look at this number right here. The group number corresponds to how many valence electrons. That shouldn't really surprise you, since we've looked at length at how the valence electron configuration is the same down groups, right? And that our number of valence electrons increases by 1 across a row. And so this should be really familiar to you. I'm just showing you that you can still know that information by just looking at the periodic table. And so next, we can start using this information to know, how do elements bond with each other? How do atoms of certain elements bond with each other? That's where we're moving toward here. So now let's talk about Lewis structures for compounds. Remember that a compound, compared to an element, compound has 1 or more atoms. It could be atoms of the same element. It could be atoms, I'm sorry, wait, don't listen to me what I just said. 2 or more atoms. Here, let me erase that and make that super clear. It has 2 or more atoms. Maybe I'll make it this color. 2 or more atoms, right? An element, if I say something about an element, I'm talking about an atom of that element. 1 atom of a particular element. Right? So if I say the element oxygen, I'm just talking about one little oxygen, but I might say something like, oh, the compound oxygen, that's actually going to be O2, which would be 2 oxygen atoms. But anyways, I just want to make sure that you understand that compounds is just when we're starting to bond atoms to each other. Okay, we've talked about that at length when you looked at the covalent compounds information. So what I want you to know is that the number of unpaired electrons in your Lewis structure that we just worked on tells you how many covalent bonds the atom needs to form to achieve a stable noble gas configuration. So what does all that mean? It means that when we actually draw out the Lewis structure of carbon, so we said that carbon has 4 valence electrons. I'm getting that from this number right here. If I was going to draw out the Lewis structure of just of the atom carbon, remember that I put atoms on each side of my invisible box. So 1, 2, 3, 4. So how many unpaired electrons does carbon have here? It actually has 4. All of them are unpaired. And so carbon, I'm going to put likes to form. Does carbon have feelings? No. But I'm just going to put carbon likes to form 4 bonds. What about if I said oxygen? Let's just do oxygen real quick. Let's do oxygen. Oxygen has 6 valence electrons. So 1, 2, 3, 4, 5, 6. Remember that I put them all around all 4 sides of the box before I double up. And so carbon has 2 unpaired electrons. Do you see what I mean by a pair? This is a pair here. So these are paired electrons. And in fact, they have a special name. They are called lone pairs. Lone pairs, like a Lone Ranger, but it's a lone pair. And so since oxygen has 2 unpaired electrons, we can say that oxygen likes to form 2 bonds. Okay, let's do some examples and see what that looks like. So in this first one, the question is, how many fluorine atoms will bond with a carbon atom? So let's look at both of these. So first, let me just write my element symbol here. Let's write fluorine and carbon. And I want to draw the Lewis structures of these first. So if I look at carbon, as we already said, carbon is going to have 4 valence electrons. So let me draw that. 1, 2, 3, 4. And so we know from this that carbon wants to form 4 bonds. We knew that already. Let's look at fluorine though. Fluorine is a halogen because it's in group 17. And fluorine is all halogens, including fluorine, are going to have 7 valence electrons. So let's draw that out. I'm going to fill it in on each side of my box before I double anything up. 1, 2, 3, 4, 5, 6, 7. So how many unpaired electrons does fluorine have? Just this one. Do you see how we have 3 lone pairs? Let me circle this is a lone pair, a lone pair, and a lone pair. It only has the 1 unpaired valence electron. And so fluorine wants to form 1 bond. And so the question is, how many fluorines will it take to fully bond a carbon atom so that they're both as happy as they could be, or both elements are as happy as they could be? Well, it would take 4 fluorine atoms, right? Each fluorine is only going to want to make 1 bond with carbon, but carbon wants to make 4 bonds. And so to make them both perfectly happy, if we put 4 fluorines around the carbon, we will end up where all of the atoms involved in this compound achieve a stable noble gas configuration because they achieve the octet rule. They get 8 electrons. And if you're like, wait, what? Let me draw it for you. So let's do our carbon atom here. I'm going to draw him in the center. He's the one who wants to make a bunch of bonds. Let me draw these bonds around here. And I'm going to draw my fluorine atoms in just a light blue color. So let me draw 1 fluorine atom that's going to bond here. Now remember, a covalent bond is where 2 atoms share a pair of electrons. So let me just say that this is going to be fluorine's lone electron, right? And fluorine has its lone pairs around here. I should have said unpaired electron, not lone electron. We don't call them that, although that's a cool name. Well, that's great. Look at this fluorine atom. This fluorine atom is perfectly happy now. It has 8 electrons around it. One of them is the one that it's sharing with carbon, right? So let's do another one. Let's do a fluorine atom right here. I'm going to put its lone pairs over here this time because this time it's going to share its unpaired electron with carbon right here. Let's do it again right next to here. It's going to share its unpaired electron, and it's got all its other lone pairs. And here it's going to share this electron, and it's going to have its other lone pairs. Look at this. Carbon now has 1, 2, 3, 4, 5, 6, 7, 8 electrons. It's got 2 electrons on each side of its imaginary box. So do all the fluorine atoms. So you see, they are very happy this way. Let me show you one other thing. Another way that people draw this is like this. You'll have your carbon atom, and then your fluorine atoms. Bear with me here. Got lots of lone pairs to draw. I hope you're double checking everything I do, making sure that it makes sense to you, that you're seeing all the electrons you should see. Let me do one more. And so what you can do is you just draw a line connecting the unpaired electrons. These are called single bonds, right? Both of these pictures represent single bonds. Both of these pictures represent single bonds. Remember that one line, one single bond, represents the pair of electrons that are being shared. Okay, the pair of electrons that are being shared. So we answered fluorine. You know, there are 4 fluorine atoms for one carbon atom in order for all of them to be happy. Let's do another couple of examples just to make sure we're really confident. How many chlorine atoms will bond with a hydrogen atom? Well, let's take a look at these 2 elements. Let me draw my element symbol first, chlorine and hydrogen. So if you come up here, hydrogen is in the first group, so it's going to have 1 valence electron. So let me draw that. And chlorine is another halogen. It's going to have 7 valence electrons, just like fluorine. Let me draw that. And just looking at this, I can say, oh, look, they both have 1 unpaired electron. They both want to form 1 bond. So I can just draw a line between them. Now, that is a hideous, very, very long single bond. So I could redraw it like this. I could say, here's my chlorine bonded to hydrogen. I could also do it like this. Here's my chlorine bonded to my hydrogen, right? Showing that they're sharing that pair of electrons. All of these would be appropriate ways to show it. So we know that chlorine and hydrogen, there's 1 chlorine atom to bond with 1 hydrogen atom. How many oxygen atoms will bond with a carbon atom? Now, here's where it gets tricky, or trickier, I should say. So we're going to have 1 carbon atom, right? So how many oxygens will we need? That's the question. So let's draw our carbon. By now, hopefully you say, oh, carbon, that's going to want to make 4 bonds. And then oxygen, let's go up here and look. Oxygen has 6 valence electrons. So let's draw that. 1, 2, 3, 4, 5, 6. Well, it's tough, right? Because let's just say that I brought this oxygen atom close to here. Let's say if I just wanted to make this 1 bond here. Well, that's great, but neither of these are happy yet, right? Oxygen likes to have 2 bonds, and carbon wants to have 4 bonds. So let's see if we can make these happy. Let's do another connection here. Let's connect these 2 atoms. Now this looks really ugly. I'm going to clean this up a little bit. Let's kind of redraw just what we've done so far. So far we have a carbon atom, and it's formed what's called a double bond with an oxygen atom. My oxygen still has these 2 lone pairs, so let me draw that. And now oxygen at least is happy. Carbon, on the other hand, still has 2 unpaired electrons. So do you see how this double bond actually made oxygen happy? But it's not quite, carbon is not quite happy here. So what do you think we could do? We could put another oxygen atom and do another double bond, right? So look, if I had another oxygen atom here with 6 valence electrons, I could form 1 bond with these unpaired electrons. It's still not happy, right? Neither of them is happy, but check this out. If I form 1 more bond here, this is ugly, but let me clean it up over here and say, oh, I see. We're going to form another, oh, apparently I can't erase. There we go. I'm going to form another double bond with my oxygen, which still has its 2 lone pairs. And so we would need 2 oxygen atoms to bond with 1 carbon atom. Let's just double check, make sure everyone's perfectly happy here. We know that a carbon atom has 4 unpaired electrons. It wants to form 4 bonds. Well, look, this carbon atom has 1, 2, 3, 4 bonds. Check. What about oxygen? Oxygen had 6 valence electrons. It wanted to form 2 bonds. So let's check. This oxygen atom has formed 2 bonds. And this oxygen atom has formed 2 bonds. Perfect. Let's just for the sake of making sure that we're really confident about our answer, we also know that each of these atoms wants to have 8 electrons around it to satisfy the octet rule, right? Well, remember that each of these bonds represents a pair of shared electrons, right? So I could sort of draw them like this, just drawing the electrons. And remember that these are all shared. So this carbon atom has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And these oxygens have 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. It might be a little bit easier to show if I draw it this other way and just show the shared electrons kind of like this. Maybe this will be a little bit easier to envision and see that there are indeed 8 shared electrons around each one. Right? So this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. And oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So they are all happy. They've satisfied the octet rule. They've made the number of bonds that they like to make. They are thrilled. Let's do one more example here. How many hydrogen atoms will bond with an oxygen atom? So we know we're going to have 1 oxygen atom. And so 1, 2, 3, 4, 5, 6 valence electrons for oxygen. Don't believe me, check the periodic table. And hydrogen is in group 1. Hydrogen wants to make 1 bond, whereas oxygen wants to make 2. Well, here right away, I think, well, I can connect this here. Now my hydrogen is happy. Remember, hydrogen only wants to have 2 electrons around it, and it's sharing this one. It's sharing this electron, and so it does have those 2. But my oxygen is not happy yet. He wants to form another bond. And so let me just put another hydrogen here. And there we go. Let me make this a little bit prettier. And there you have it. We want 2 hydrogen atoms for 1 oxygen atom.